Okay, welcome to this numerical solutions of ordinary differential equation, which is chapter 6. So I think let us see differential equation. Actually, in previous calculus or mathematics background, you know ordinary differential equations. I think it is just great importance in engineering practice. This is because many physical laws are coached in terms of this rate of change of velocity or quantity rather than magnitude, etc. And also rate of change of population forecasting, for example, and also the acceleration of a falling body, which is rate of change of velocity. So I think you will apply different methods, and two types of problems may be addressed, such as initial value problem and boundary value problem. So as much as possible, we have to consider such aspects in every mathematical background. And partial differential equation also, I think it is used to characterize engineering systems, for example, and where the behavior of physical quantity is coached in terms of rate of change of something with respect to two or more independent variable. Okay, so before I go through the detail, let me speak few points on learning objectives of this chapter. At the end of this chapter, you will be able to solve ordinary differential equations with any format, and you will be able to appreciate the importance of numerical methods in solving ordinary differential equations, and also know the relationship of Euler's method to the Taylor series expansion, and know how to apply any of the arcane methods, Runge-Kutta method, to systems of equations, and you will be able to reduce an nth order ordinary differential equation to a system of n first order ordinary differential equation also, and just in the form of Runge-Kutta method also, you will just form first order, second order, third order, and fourth order can be made. And you will understand the derivation of the second order arcane method and how it relates to Taylor series expansion. And you will understand also the difference between initial value and boundary value problems. And I think recognize this type of problem context where the step size adjustment is important, then you can check. So these are the main learning objectives of this chapter. So I think ordinary differential equation is very important in engineering fields. So we will see the detail now. Let us see. So as introduction, I think just this ordinary differential equation, you have something very nice approach. So just it is abbreviated as ODE in mathematics. It is an equation which consists of one or more functions of one independent variable along with their derivatives. So you may have derivatives and one independent variable. So it is composition. So how do you compute? So we will see. So a differential equation is an equation just that contains a function with one or more derivatives. You see, just a function with one or more derivatives. So, but in the case of ODE, the word ordinary is used for derivative of the functions for the single independent variable. So we will see the detail. So the ordinary differential equations are of great importance in engineering practice also. In engineering practice, just it has many applications. So we will see this one because many physical laws are coached in terms of rate of change. This is very important issue, rate of change of quantity rather than magnitude. So we will focus rate of change rather than magnitude. So how the rate is changing, we will focus. So rather than the magnitude of a quantity by itself, we will see the rate of change of a quantity. For example, rate of change of population. This is one example, very nice example. Rate of change of population and rate of change of velocity, which is For example, the acceleration of a falling body, something like that, just dv by dt, etc. So partial differential equation also, very important topic. We will see the detail. Just it is used to characterize engineering systems where the behavior of physical quantities coached in terms of rate of change with respect to something, with respect to two or more independent variables. And the solutions of this ordinary differential equation, again, I think, can be found in an easy way with the help of integration. So we have the integration background from calculus, then we will see how to solve such equations. Okay, so ordinary differential equations involve one or more ordinary derivatives. So we will see this one in detail. So just unknown function, derivatives of unknown function with respect to one independent variable. One independent variable. You have one independent variable. So numerical methods for linear differential equations calculate the solution on points where h is the step size. You can find Tn. So this Tn, I think, important topic, can be found. So this Tn, any, just it could be variable. So we can find with h step size. So I think differential equations we can categorize into ordinary differential equation or partial differential equations. So differential equations, either of these. So ordinary means just as I speak previously, just it involves one or more ordinary derivative, but with some one independent variable. So you can see, for example, d square v divided by dt square plus 6dv is equal to 1. So this is, I think you can see now, this equation is, I think it holds one independent variable and something you have derivative d square v. So it involves one or more ordinary derivative you have and unknown functions of unknown functions. But partial differential equation all will be something partial derivative. So del square u with respect to del y square, again you can see this one, and we will just solve something like that. So I think you know Laplace equation. I think with partial derivation we can see in fluid mechanics again we have velocity potential, something like that. So we can just go through that. So it involves one or more partial derivatives of unknown functions. Something unknown you have, then you will focus on that. Okay, so what are classifications of ordinary differential equations? It may be classified as, for example, order. Order means just it could be second order, first order, or something first order. For example, you may have first order, or sometimes second order, and something like that. So you have order of derivatives, and homogeneity. You may have homogeneous, non-homogeneous, etc. Linear and non-linear. And auxiliary conditions, it could be initial value problems. All conditions at one point of the independent variable can be found. For example, you can see this equation y prime of t is equal to f of yt. Then initial condition you have here. This is the initial condition, which is y of 0 is equal to y naught. So x naught is this one. So x naught will be this value x naught. Then I think you have initial condition. Then you can proceed to the final point, any point. So it could be just x double dot is just second derivative plus 2x prime x dot plus x is equal to e the power of negative 2t. Then x of 0, 1, x dot of 0, 2.5. Then you can proceed like that. I think this is important issue. We have initial and boundary value problem. Sometimes you may have at the end points we have some values, and we can just approximate, or we can derive the equation. So the conditions are not at one point of the independent variable. So these are one classification of ordinary differential equation. And single step method and multi-step method also as a solution, we have a category. So I think we have such condition, and as example, we can see just d square theta dt square plus omega square theta is equal to 0. I think the same theta of 0 is equal to theta naught, which is this is initial condition, d theta by dt, which is at 0, 0, then we can have something just second order and third order differential equation. Second order, which is order of ODE, then linear, it is just linear, homogeneous ODE, and initial value problem, because we have initial condition. And the second one is nonlinear. You can see just nonlinear equation because we have sine theta, then it is nonlinear, homogeneous, and initial value problem. So what are numerical methods for ordinary differential equations? What are numerical methods? So we have around 8 methods of solving numerical solutions of ordinary differential equations. These are, the first one is, you can see just Taylor method. Taylor is the first one, and the second one is just the Euler's method. We have again modified Euler's method, Runge-Kutta method, and the fifth one is Picard's method, and we have again mildness predictor corrector method, and correlation and regression, and we have again here curve fitting. So I think these are the methods of solving numerical solution of ordinary differential equations. So we will focus on the first 4, and I may include some Picard's method or mildness predictor method in a tutorial problem. So let us see the detail now. The first one is Taylor method. So in Taylor method, I think you have something from the previous Taylor series expansion, you have highlight. So we start from this condition. This is the condition, which is dy by dx is equal to f of xy, which is the derivative of y with respect to x is f of xy, with initial condition, which is y of x naught is equal to y naught. This is initial condition for the starting point. Then we will calculate the next equations. We will calculate the initial. Then we will go to the detail. So this is the general equation. You can see this is the general equation. This is the general equation, which is y of x is equal to y of x naught, which is y naught plus x minus x naught, y prime of x naught plus x minus x naught square over 2 factorial, second derivative, then y naught, etc. So this is, I think, already we just calculate from the previous topic. So you have here, you have x is equal to x naught plus h. Put h in x minus x naught in the above equation, in this equation, then you will find h. In terms of h, you can write the equation, which is any y of x is equal to y naught plus h y prime of y naught, y prime y naught, then etc. You can find. Then finally, we will go to the solution. Any point can be calculated. So we start from this one, which is y of x naught is equal to y naught, y of x1 is equal to y1. Similarly, you proceed. So after substitution, for example, for y1, for the first calculation, you have here y1, which is y naught, which is you start y naught plus h y prime y naught, then h square, etc. You proceed up to higher order derivatives. You can proceed. It depends upon the equation. And you can see this one. This is again y2. y2 again, you take y1 from the previous calculation, then you insert here, then you go to y3. y3 again, this is y3, y2 plus h y2 prime, etc. Second derivative, etc. Then this is a general equation. This is a general equation for Taylor series method for differential equation. Yn plus 1, yn plus h yn prime plus h square over 2 factorial, y double prime n, h cube over 3 factorial, y third derivative n, etc. Where n starts from 0 because we will have y naught initial condition, you start from that, then we will calculate other values. So we can create the solution. Okay, second method is Euler's method. So similarly, we will consider the first order differential equation, which is dy by dx is equal to f of xy with initial condition, which is initial value, y of x naught is equal to y naught. Then to find y of xn, then you can have yn. Then from forward difference approximation of the first derivative, I think we know this equation from the previous topic, or from derivative of the function yn, derivative is equal to yn plus 1 over minus yn over h step size. So this is the equation. Then you can have h is just the step size tn plus 1 minus tn, or in terms of x, if t is variable, it could be, and h equal to xn plus 1 minus xn, where n is 0, 1, 2, etc., because we will start from x naught. Then if you rewrite the above equation, then you can have this equation. This is the equation. After rewriting the above equation, you have this one. Then y prime n is f of xn yn, which is derivative from the above. So according to Euler's method, you have these equations. So we will have Euler's equation, yn plus 1 is equal to yn plus h step size f of xn yn, n which is 0, 1, 2, etc. So f of xy will be given, then you will substitute accordingly, then you can find the next step. So yn, you can use this one also, if n is 1, n 1 if you substitute, y naught, this will be y naught, otherwise you can use either of the formulas. So this is just the formula for dy by dx, then you can have any successive values will be computed. So you will start from initial condition, which is initial y naught, x naught and y naught known. Then you can start with every step size. You can calculate y1, y2, y3, y4, etc. for a step size h equal step size. Okay, modified Euler's method, again, instead of approximating f of xy, which is just a function, which is dy by dx, by this one, in the above equation, we approximate by trapezoidal rule. So this is by trapezoidal formula, which is h over 2, which is f of x naught and f of x1, y1. You start from this. From this, we can start, which is the mean of the slopes of the tangents at the points corresponding to x is equal to x naught and x is equal to x1. Using this value of y naught, you can find y1. So y1 will be computed by this one. By approximating this value, you can find y1. So this is y1. So once you calculate y1, then you proceed like that. So y1 with initial condition 0, you can have y1 is obtained from Euler's method, which is y naught plus h f of x naught y naught. Then next, to find y of xn, yn, you can proceed y1, y2, etc. You just proceed with that one. With this equation, with this algorithm, you can have f of x naught, y naught. Every step you substitute, then x1, y1. Then y1 of is this step, is above step, you proceed. Then you can find the solution. So according to modified Euler's method, this is the algorithm. You can use this algorithm. This is the algorithm. I think we can apply yn plus 1 is equal to yn plus h over 2 z trapezoidal rule, which is yn prime derivative is f of x and y. So for every step you can find according to modified Euler's method. And Runge-Kutta method, this is a very important formula in ordinary differential equation. So the RK methods do not require the calculations of higher order derivatives, and they are designed to give greater accuracy with the advantage of requiring only the function values at some selected points of the sub-interval. So we need what? Some just function values. If you have y0, y1, y2, etc., then we will apply this Runge-Kutta method. So Runge-Kutta method, you have 3 steps, I think 4 steps. So first order RK method, which is similar with Euler's method, you will apply Euler's method directly. Yn plus 1 is equal to yn plus h f of xn yn. N starts from 0, 1, 2, etc. So dy by dx is given, then some function value of f of xn yn, then you can substitute, proceed, just at n0, at n1, etc. Every step value will be completed. We will have example on this. And second order RK method, again, similar with the modified Euler's formula, which is trapezoidal rule. You will add trapezoidal rule here. Trapezoidal rule will be added. F of x naught, y naught, plus f of x naught plus h, which is a coordinate. This is just h times this one, which is Euler's method. Then you can have k1 and k2 value, which is just average. We'll take k1 and k2. So for y1, to compute y1, just you have k1, k2, then k1 is h into f of x naught, y naught, and k2 is h times f of x naught plus h, y naught plus k1. K1 will be added to the second coordinate, then you find that this is the first approximation. Second approximation, you proceed like that, and then you arrive at the solution. And third order RK method, I think you will go to the third k up to k will be up to 3, which is this is the solution for the first approximation. If you have y naught is given, then 1 over 6 k1 plus 4 k2 plus k3, where k1 is h into f of x naught, y naught, then k2 is previous h times f of x naught plus h over 2 plus comma just y naught plus k1 over 2. This is second coordinate. Then once you get k2 and k3 will be completed. So k3 will be just you will find k3 here h into f of x naught, then plus h y naught plus k prime, then k prime is h into the previous one. You add just k1. So I think this is the Runge-Kutta third method, third order formula. And fourth order RK method is very important. Working rule. You have for solving initial value problem. Already working rule we have for initial value problem. You have this one. dy by dx is equal to f of xy, which is y of 0 is equal to y naught, means x naught. You are taking x naught here. In this bracket, you have x naught. This is x naught. Clear? So I think the fourth order Runge-Kutta method is this is a formula, general equation, which is you can apply yi plus 1 is equal to yi plus 1 over 6 k1, which is weighted mean of all k's, plus 2k2 plus 2k3 plus k4 times h. So I starts from 0, 1, 2, etc. Yn plus 1 is equal to yn plus k. So the first approximation, when n is 0, y1 will be approximated. Once you calculate 1 over 6 of this, then y1 will be completed. Then you go again another step. Then you have. So this is the weighted mean of k values. Then calculate k1 first, h into f of x naught, y naught. In the equation, you substitute x naught, y naught. Then k2, you bring here x naught, then h over 2, y naught plus k1 over 2. k1 already you have here. Second coordinate will be used this one. Then second, once you calculate this one, then third again, then fourth again, you can calculate. So finally, we will take the mean of this, then divide by 6. You get the first approximation. Okay, how to write ordinary differential equation? How does one write a first order differential equation in the form of dy by dx, which is f of xy? Most of the time, equation may not be direct. For example, dy by dx plus 2y is equal to 1.3 e to the power of negative x, y of 0 is equal to 5, and find y of 0.1, y of 0.2. So you can apply either Euler's method, etc. So the first step is solution. Just rearrange. Bring dy by dx in the left side and the expression in this side. So this is the expression. 1.3 is the power of negative x minus 2y. Y of 0 is this is initial condition is equal to 5. Then you get what? F of x1 according to the working rule. According to the working rule, you have this one, which is very important, f of xy. Then from y of x naught is equal to y naught, which is initial condition, then x naught is 0 because you have here x naught, which is this one. So this value is important, which is x naught. Clear? Then you start from that, which is f of x naught, y naught, etc. According to Euler's method, according to Runge-Kutta method, you can apply, or Taylor series expansion, you can start. So I think this is nice. We will see examples. So as a reference, as usual, please go through Stephen Chapra, Raymond in Canal, Numerical Methods for Civil Engineers, 8th edition, and Richard Barden again. This is very nice book. Numerical Analysis 10th edition, and B.S. Grewal, Numerical Methods in Engineering and Science, and Ravish Arsingh Mukhal Bahar, Complex Variables in Numerical Methods, Gujarat Technological University, 2017 second edition. This is very nice, and please go through this again. This is very nice. Just link http just /numericalmethods.eng USF and you can apply this one. I think if you have any question, you are welcome. Otherwise, ጥያቄ ካላችሁ ፕሊዝ አስቀምጡልኝ። ወደ ኤግዛምፕል እንሄዳለን። Thank you very much. Okay, thanks for watching this video. If you have any question or doubt regarding this topic, please write down in the comment section below. I will reply on it. Thanks again.